So welcome to Unit 1, Lesson 2, which covers scientific notation. So the goals here are to be able to express numbers in standard form, more commonly known as scientific notation, and to be able to perform operations with numbers in this form. So for example, to multiply or divide numbers in this form. So in order to accomplish these goals, we need to know about the format of scientific notation and how to interpret these values and convert between them. So we'll start with some real life examples. The main purpose of scientific notation is to be able to efficiently represent really, really large or really, really small numbers. And it allows us to write these without having to write a lot of zeros. So hopefully these examples will illustrate what I mean here. So an example of a quite small number would be the mass or weight of a human cell. So this can be represented as that value, 0.00000000035 grams. Kind of onerous to write this number. In scientific notation, we can write it as 3.5 times 10 to the negative 9 grams. Much more efficient. Another example on this side, in this example, a very large number would be the mass of the Earth in kilograms. And that value is 5974 followed by 21 zeros. So you can imagine, again, not terribly efficient to have to write it out this way when you want to communicate this value. In scientific notation, it becomes 5.974 times 10 to the 24 kilograms. The last example is how many tweets are sent per day, and that works out to be 500 million. Again, in scientific notation, that just becomes 5 times 10 to the 8. So scientific notation has great advantages in efficiency. And there are some standardized rules for how to communicate a number in proper scientific notation. So the key thing about scientific notation or standard form is the format. And the format looks like this. Some number a multiplied by 10 to the exponent k. And there's some key things to know about each of those values. So the value a has to be greater than or equal to 1, but less than 10. So for example, you'll see in the weight of a human cell example, the scientific notation coefficient, or A value, is 3.5. So that's between 1 and 10. The next example, 5.974. And the final example, A equals 5. The other important feature is that K, or the exponent, must be an integer. So K cannot be a decimal or a fraction. It can be either positive or negative. As you can see in our examples, the first one has a negative exponent, the other two have positive exponents, but it can't be a decimal or a fraction. So some patterns seem to emerge. Positive exponents appear to apply to very, very large numbers, whereas the negative exponent seems to apply to a very small number. So one thing, we need to sort of keep these things in mind when we're converting to and from scientific notation. So let's try some conversions as an example. So if we look here, we have some numbers we can try to convert to standard form. So we'll do the first example, which is 257 million. So when you're converting, a good rule of thumb is to look for the first significant figure in the number or in the value. And that was basically saying look for the first non-zero digit. So when we look here, the first non-zero digit is the first digit of the number, which is the 2. So we start with that first significant figure, and we're going to place our decimal after that first significant figure. That ensures that our A value is going to be between 1 and 10. So if we put the decimal after the first significant figure, I know I'll get a number greater than or equal to 1 and less than 10. I then write the remaining significant figures or non-zero digits. So that would be 2.57. So that's my A value, 2.57. Every number in standard form or scientific notation is then followed by times 10. Always. You always have that as part of your number. Now I have to figure out what my exponent is. And to do that, I kind of imagine if my decimal is between the 2 and the 5, how many decimal places do I have to move to return to the original number? So I'll just show some rough work at the bottom. If I start with 2.57, how many places do I have to move to return to the original 257 million? So I move 2 spaces to get around the 5 and the 7. And then I'd have to move 6 more places to account for the zeros. 1, 2, 3, 4, 5, 6. So in total, to return to the original value, if I start with 2.57, I move to the right 8 places, which means my exponent is going to be positive because I've moved the decimal to the right 8, because I moved 8 decimal places. And that's your conversion. The process for a really small number or an original value less than 1 is very similar. So for example, B, starting 0.00043. So I'm going to go through a very similar process. I'm going to find my first significant figure, my first non-zero digit, and that is the 4. So I'm going to start with the 4, and the decimal is going to be placed after the 4. But 4.3 is my A value. And if I start with 4.3, I'm going to go through the same process. How many decimal places do I have to move to get back to my original number? Now, the interesting thing here is I have to move to the left to return to my original number. So I move to the left once to get around the 4, and then I'm going to move 3 more times to account for the zeros that will exist in that number. So in order to start from 4.3 and return to the original value, I have to shift left 4 places. So I still have the times 10 because that is always there in scientific notation. And now I have a negative exponent because I moved to the left or because I have a very small number, and a 4 because I moved 4 places. Look at the third example. It's kind of interesting. It looks like it's already in scientific notation. It has times 10, the exponent is an integer. The issue is that this number is not between 1 and 10, less than 1. So we have to convert that. And I think the most straightforward approach is to convert that number individually. So if we were to convert 0.23 to scientific notation, it would be 2.3 times 10 to the negative 1, because I'd move 1 to the left to return to 0.23. But then I still have this quantity multiplied by 10 to the 3. Then I can just use some exponent laws. When I have 2 expressions that have the same base of 10 and different exponents, I can just add the exponents together, and that's what my value would simplify to. So when you're converting, always look for where your first significant figure is. Make sure your A value is between 1 and 10, or greater than or equal to 1 and less than 10, and make sure your exponent is an integer that accurately reflects how to return your original value. So one thing to think about is that a positive exponent, like in the first example, is like multiplying by 10 over and over. So your number should get bigger. If I start with 0.57 and I have a positive exponent, end with a really large number. If your exponent is negative, that's like taking your a value and repeatedly dividing by 10. So if I start with 4.3 and my exponent is negative, I should be getting a number that's smaller and smaller, which makes sense with my original value. The last thing to keep in mind is what standard form looks like on your GDC. So if you perform operations with standard form on your GDC, you get an answer that might look a little bit different than what you're accustomed to. Really important to be able to interpret this notation because you can't use that notation for your answers. So on your GDC, you might often see scientific notation answer written like this, 3.9 E06. Basically, the E represents the times 10, and the 06 represents the exponent of positive 6. So when you're writing a response on your test, you have to remember that this calculator notation is not an acceptable format for your test responses. So you have to sort of keep that in mind when you're working through these examples. So if you were to go through and do some operations with scientific notation, you should be able to just type them into your calculator and then use that to figure out the response. So the first one, 875,000 multiplied by 95 million. So when you do that on your calculator, if we write our response in scientific notation, you should get 8.265 times 10, and because it's a very large number, it's going to be to the power of 13. And that's going to be your final response. And you should be able to do something similar with division. So if you're presented scientific notation, you can type it into your calculator and then divide numbers. Sometimes I just break it down. And I know that for this one, it'll be 6.2 divided by 8, which is 0.775, multiplied by 10, and I can just apply my exponent law. So 3 minus 12 is negative 9. And again, my a value doesn't quite fit, so I'm going to have to change that to 7.75 times 10 to the negative 1, and I'll simplify that answer at the end. You don't have to approach it this way. You can just type it into your calculator and get the answer, but you should get 7.75 times 10 to the negative 10. So hopefully now you know the properties of scientific notation, and you can convert to scientific notation and perform operations, and should be able to tackle the homework from here.